In today's lab, we're going to be making a power supply that provides 5 volts regulated power from a 9 volt unregulated single supply. And before demonstrating though, let's review the schematic and have an overview of the breadboard. So this is going to be broken up into 4 parts: the Zener voltage reference, here, the op-amp that controls the circuit here, the transistor, and finally the feedback which allows the op-amp to do its job. The Zener voltage reference is a 3.3 volt Zener, and Zeners need a current sufficient to get them past the knee on their curve and into the region where their voltage output is relatively flat. And the data sheet uses a value of 5 milliamps, and we'll do the same. So to get that 5 milliamps, we're going to use a current limiting resistor. Shown here in the schematic is R1. And the calculation then to determine a value of roughly 5 milliamps just uses Ohm's law. We know that the voltage across that resistor is going to be the 9 volt unregulated input minus the 3.3 volts provided by the Zener diode. And we only need to divide that by the current to calculate the resistor value. If we do that, we come up with a value of 1,140 ohms, which we'll round off to 1,000 ohms, just to use a common value. And that'll give a current somewhat greater than 5 milliamps, but that should work fine. Now, that output then is the input to the op-amp on the non-inverting pin. And since an op-amp wants to keep the inverting and the non-inverting pins, the difference between them, as close as it can to 0 when set up for negative feedback, well, we just need to remember that this pin and this pin are going to be both at 3.3 volts. Now the LM358 is a dual op-amp, so there's 2 op-amps in the same IC. Well, we'll be using the first one, and the second one will not be connected. The output of the op-amp will go to this particular transistor, which is a 2N3904. The 2N3904 is an NPN transistor. It can supply about 200 milliamps. And we'll be testing up to about 100 milliamps just to see how the power supply behaves. Now we desire a 5 volt output. And we know that through the op-amp action, when the op-amp is set up for negative feedback, that the inverting pin is going to have the same voltage as the non-inverting pin, in this case set at 3.3 volts. So we're going to have 3.3 volts here. And we want 5 volts here on the output of the transistor. So knowing that, we can set an arbitrary value of 10,000 ohms here. And this particular resistor then, of course, we'll see 3.3 volts here, and it'll be grounded there. So we know that to be 5 volts. We know that resistor. This is the unknown. We can then use the voltage divider equation to calculate a value for this, which will give us approximately 5 volts out. And if we do that calculation, we'll come up with something like, in this common value here, of 5K1 or 5100 ohms. So that's the circuit, and what we'll be looking for again is volts, 3.3 volts here, 3.3 volts there, 5 volts there, and that should be relatively constant or regulated regardless of the value of the input rail and regardless of the current that's being drawn by our load. So here's a quick review of the breadboard. The current limiting resistor, resistor 1, is here. The diode is located here. The IC is here. Pin 8 is connected to the unregulated power. Pin 4 is connected to ground. The non-inverting pin is pin 3. The inverting pin is pin 2. And the output is on pin 1. The transistor is located here. And pin 1 is the emitter. It's connected over here to the output as well as the voltage divider, and pin 2 is the base connected to the output of the IC, the op amp, and pin 3 is the collector connected to the unregulated power. Here's the voltage divider. R2 is the 5100 ohm resistor. R3 is the 10,000 ohm resistor. And again, the output from the voltage divider returns back to the op amp on pin 2. And that's the circuit as we've arranged it on the breadboard. Give me just a second and I'll move the camera so that we can do the demonstration. Okay, I'm back. So we're ready for the demonstration. I'm going to do a couple of things. First, I'll go over the setup with you, and then we'll investigate the influence of load on the breadboard power supply. And then we'll look at the influence of changing the input power rail, the what's called V+ on the schematic here. Now, as far as the setup, it's pretty simple. There's a bench power supply here, and it's currently set up to deliver 9 volts, which was the design point for our power supply that's on the breadboard. It also has a rather inaccurate but useful display of current. Right now it's showing 3 milliamps. And if you'll remember, our design of the Zener diode was to get about 5 milliamps through that Zener, and I believe that this is a bit inaccurate, and we actually are getting something in excess of my 5 milliamps through the Zener diode. Okay, and here we have a bench multimeter, and it's measuring the difference between ground and the output of the breadboard power supply. And it's showing 4.87 volts, which is pretty close to the 5-volt design. Remember though that our parts, our components, had some variance in them. The Zener diode having the largest, it's a plus or minus 5% part. So this 4.87 volts that we're seeing on the output of our breadboard power supply is well within, the kind of thing that the kind of changes that we might expect just from this Zener diode alone. So just to prove that, I'm going to measure with this little multimeter, which is also measuring voltage. the Zener voltage. Okay, it doesn't want to behave here. Sometimes it needs a little help. Try again. There we go, 3.24 volts. Remember again, our design was 3.3 volts, so it's a bit low. And I think we're seeing that make its way through our circuit here to the output, which is a bit low as well at 4.87 volts. Now, this doesn't have a load on it at the moment. And the first kind of test we're going to do is what is the influence of the load on our breadboard power supply. And I have 3 resistors down here. The first one is a 4700 ohm resistor. And if you do the calculations assuming a 5 volt power supply, remember we're a bit lower, 5 volts, you'll get 1.1 milliamps. And using Ohm's law, if we go through a 470 ohm load, we should get about 11 milliamps. And for a 47 ohm load, we should get around 110 milliamps. So let's just test that out. We'll start with the 4700 ohm load. There we go. And just a quick look here. Our voltage output hasn't changed at all. It's still 4.87 volts, but we see a slight bump up of 1 milliamp, which is what we expected from this particular load. We're seeing current flow now through the transistor, and it's about 1 milliamp. All right, let's try the next load. This one is 470 ohms, and we're expecting about 11 milliamps. Again, our voltage output is not changed. It's 4.87 volts. Our current is now 13 milliamps, so it's up about 10 milliamps. So in the ballpark, again, this is not real accurate, and we're not at 5 volts. We're at 4.87. So let's remove that load and go to 47 ohms, which should require our power supply, our little breadboard power supply, to put out about 110 milliamps if it were 5 volts, but it stayed at 4.87, so it's really doing good here as far as regulating voltage with a fixed input voltage of 9 volts, and it's now showing 108 milliamps, which is something over 100 milliamps delivered through the transistor. So that's really good. It does, if provided that the input voltage is rather constant, it will, with loads up to let's say 100 milliamps, performs quite admirably. But at some point it probably falls apart. Let's just bump it up to 1 amp and see what happens.
I'm giving her all she's got, Captain. She can't take any more.
Damn. Chekhov, reroute auxiliary power to the helm.
Scotty, the bridge. Captain, this is a little embarrassing, but you know, I've never noticed the little lever I've been pushing. It's only about 2/3 of the way up. I actually can give her more.
That's great, Scotty. Mrs. Spock, give us readings on...
Captain, Scotty again. Yeah, you're not going to believe this. There is another lever here too. The ship can literally go 3 times as fast. I'm sorry, but I feel like such a capital J jerk right now.
It's okay, Scotty. Lieutenant Uhura, open all channels for...
Captain, I've got to interrupt again.
No, just kidding. We're not going to do that. What I will do, though, I'm just going to take this load off and drop it back down. This, actually gets pretty warm, although it can handle it all right. I'm going to drop it down and use a 470 ohm resistor. which again is about 10 milliamps. And what we'll do is change the input voltage, which is shown as V plus on our schematic, to the breadboard power supply to simulate what might happen if, say, a 9-volt battery dropped down to 7 volts. So it's at 9 volts right now, and we are seeing 4.87 on the output of the breadboard power supply, and I'm going to move it down to 7 volts on that input positive power rail, and we see a drop down to 4.65 volts. So remember that 4.65, I'll move it up to 9 to 4.88, 4.87. So what's happening here? Well, we can get a better idea if I increase the voltage up really high on the input rail, or the voltage that's being delivered by this bench power supply. What I'm going to do is increase it a full, let's say 10 volts, and we'll see what happens. How well does it hold this 4.87 volts here? Well, I think that's pretty unreasonable, but I've increased it 10 volts, and it's gone from 4.87 up to 5.45 volts. So what's happening? Well, if we go and probe the Zener voltage is 3.6. So it's gone from 3.2 something up to 3.6 volts. And again, let's just move this down to 9 volts again and watch the Zener voltage drop. There's 9 volts. And 3.2, I think it's going to end up around 2.23. Yeah. So, yeah, that's what's happening. Our Zener diode is moving farther away from the knee of its curve. That's the so-called Zener impedance. And we're seeing the voltage of our voltage reference shift, which causes the voltage output of our breadboard power supply to shift as well. And I'll do a little calculation in the notes that follow to show how that works using data from the data sheet. One more thing I might just show real quickly here is, since I'm measuring the Zener voltage, which also just happens to be the voltage to the non-inverting pin on the op amp, is to measure the inverting pin, and we ought to be getting 3.23, 3.24 when we do that. So let me just move it over there and demonstrate that those are the same. 3.23. So indeed, op amp action, op amp magic does occur. So that's a demonstration. I hope you enjoyed it.